This is something that you don't normally see. I'm showing you the spectral response, and this is the actual measured spectral response of the Genesis camera. And I'm going to show you some other color filter arrays, actually a very good still camera made by Canon later. But immediately, what you're seeing here, which is not normal, is you're seeing the peak transmission, which, as you see, is about 50%. This is a 2/3 inch camera that uses a prism. And two things are immediately obvious. The slopes are much sharper. What we call the crosstalk, the crossover regions are much smaller than here and here, and here and here. And they're much narrower, but they're also much more efficient. You see, we're getting close to 90%. So when you're building a camera with a color filter array, because these are pigments, basically, literally lithographically printed on top of the pixels, the choice of the color saturation of these devices basically determines the sensitivity of the camera. We get away with that for a reason that I'll show you later, which has to do with the super 35mm sensor size. Another issue that I was asked to address is how do we color balance a camera? These two graphs, this is the spectral power distribution of what we call illuminant D65. That's not sunlight, which is usually considered to be 5,000, 5,500 Kelvin. This is this is skylight, which is a combination of sunlight and the blue sky. And this is standard illuminant A, which is warmer than 3200. It's 2856 Kelvin for those who care. And it's actually much more likely, if you actually make a real color temperature measurement in the studio, you're more likely to get this number than the 3200, unless you put a transformer to boost the... So the problem that we have to deal with a digital camera is, this is what we'd really like. We'd like to have equal blue, green, and red. And I've sort of centered these in the peaks of where the color analysis normally goes. And the way I like to think about these when I'm color balancing the camera is I like to think about this as a beam balance. Now, right now, it's balanced. And we don't change the green. We're going to pivot around the green. So the blue will go up or the blue will go down. So basically, this is what happens if we're going to shoot with that camera that's perfectly balanced in terms of its outputs to an arbitrary light source that doesn't exist, that has equal value in red, green, and blue. And what you see is that you have very little blue light. So in order to color balance this camera back to equal, what we need to do is we need to boost that blue signal. In fact, we need to double it. There's about 6 dB of gain on the blue channel on any CCD or CMOS camera if it's balanced for tungsten. There's 6 dB more gain in the blue channel. And of course, we've got a surfeit of red and infrared, and we need to reduce the gain in the red signal. If we balance for daylight, of course, we've got all the blue in the world, and this camera will appear to be less noisy, but of course, I would think that from a practical photographic standpoint, most of the time we're working, or not most of the time we're working with tungsten light, but that's the light source of which we have the least amount of light. When you're outside in daylight, usually, you've got lots of light. So in this instance, what you do is you actually decrease the blue gain and you increase the red gain. This is not, linear or, shall I say, logarithmic, but basically you'd have to increase the red gain about 2.5 dB and reduce the blue gain somewhat similar. So most traditional electronic cameras are naturally balanced for tungsten because that's the worst case. But that's also where you will get the most noise. So you have to be careful when you measure signal to noise that you understand how the camera is color balanced and color balance it appropriately for the light source that you're using when making the measurements. Someone was asking me about earlier on about film. You know, when you project film, because it's not bandwidth limited, if you get closer to the scene where you see more information. This is the curves that were created from that little test target that I showed you earlier on that we use, which automatically generates a curve. This actually was from the prototype Genesis camera during the shoot that Alan Davio did when in May 2004, I think. And what you see, and this is one of the issues with the electronic camera, all of the convolution of the various elements necessary to get to the film negative are basically eliminated with a digital camera. So you get a free ride. You get more MTF from a digital camera because you don't have in the case of the 5218 negative, it had to be rephotographed onto another CCD with another lens, you know, the printing lens. So this is what you're seeing here, and this is when people have looked at these images and have questioned why does the digital image look so sharp, it's because you have reduced the number of components in that MTF equation. This is one of my favorite cameras. It's getting quite old now, but you'll see a similar response characteristic, and there's quite a bit of crosstalk. This, of course, is a Bayer pattern camera. That has nothing to do with the actual color. But cameras like this camera and modern digital still cameras use very sophisticated algorithms to process the Bayer pattern. And in fact, you know, whenever we've made measurements with these cameras, they seem to exceed Nyquist. I mean, they do a remarkable job. Of course, they're not really, and in fact, your explanation of the diagonal sampling is really what's going on. But it is quite, you know, it's quite remarkable the performance you can get from these. However, the problem is there are residual aliases, and these cameras use image processing that is contextual. In other words, it can understand that it's looking at sky and greenery or a graphic and processes and can process accordingly. Digic 3 is a new processor, I believe. The 3-sensor prism system, I'm only mentioning this because I'm going to show you a camera that is a true 4K camera, and it uses a prism system, and it uses 3 CMOS sensors that were developed by, believe it or not, by Panavision Silicon Video Imaging. And each of the sensors is 3840 by 2160. But this is a general, this is the original Philips prism, and I've actually went to the trouble of making sure all these angles are correct because most of the published stuff isn't. Now, the difference in efficiency between the color filter arrays and the interference filters in the prism, this is where we make it up. This is a 2/3 inch sensor in scale to the Super 35 sensor, the Super 35, the D format in film, which is 16 by 9, 27.5 millimeter diagonal. This is the same sensor size as Genesis. As I said before, I've been using this little picket fence to illustrate this frequency response issue for a long time. This is half the Nyquist limit. You know, Larry was talking about the Nyquist limit on the 2/3 inch sensor being 100 cycles per millimeter. What we try to do is, again, optimizing for these lower frequencies, we always try to optimize to get the highest contrast at half Nyquist. And so 20 cycles for this big sensor. So it really makes the job for the lens designer a lot easier than the guy that has to do this. Because the Nyquist here is 40 cycles and here it's 100 cycles, and it's very, very hard it's much harder. You need to have a lens that's 2.5 times as good to cover that little 2/3 inch format compared to this big film format. And it takes 6 of those to match the area of this, which is where we make up the difference in optical efficiency of the color filter array versus the interference filter. And this is Super 35 film, and this is Super 35 sensor. Actually, this is a new sensor. It's not the sensor that's in Genesis, it's a CMOS sensor with 37.5 million pixels. This is the Genesis structure, and as you see, what it is stripes. If you ever take a magnifying glass, if you've still got a Trinitron CRT, you'll see that the stripes line up like this. And it's 5,760 pixels by 2,160 pixels. And but what we output is 1920 by 1080 RGB. So if you wanted to, you could say it was a 6 megapixel or a 6K sensor, but really, you know, it's a little bit like, well, you know, I weigh 200 pounds. It's a lot better to say that I weigh 80 kilos. Just this nice number. Here is your, this is a discussion that we have to have, but for sure, in a Bayer pattern, the issue is that you have twice as many greens as you do have red and blue. And for any operation where you need equal bandwidth, like shooting blue screen or green screen, we really prefer the 444 sampling. It always makes me laugh because most of the studios out there are insisting for features that record 444. But of course, if you start off with 422, what you're basically doing is interpolating to create the other half bandwidth. Plus the fact that in this stripe configuration, a DPX file is 8 megabytes. This is 32. So, whatever you want to image process, but you're processing, a lot of empty pixels for no more spatial resolution. This, by the way, is a true 4K camera, or using the new math, a 12K camera. And that's the camera that uses the 3840 by 2160 pixels. The images from these, by the way, and I should have thought to put one of the images in there. The images from these, it doesn't have the dynamic range of, or at least the scene dynamic range of a motion picture film, but it does have a spatial resolution that you will see. The only film format that looks anything like it is IMAX. This, of course, is the camera head, but there's a whole parcel of electronics, and nobody's going to be putting this in a Steadicam anytime soon. But you have to remember, that the predecessor to the Genesis camera was in 1991, the HDC 500, which was a 3-chip 1920 1080 camera. And that camera and its processing weighed about 200 pounds. The camera head was very small, but all the associated processing. So, in 10 years, we will certainly see cameras like this being, mounted on the shoulder or Steadicam near you. And I think that's it for me. Thank you very, very much.